Yeah, we'll start every 2 or 3. All right. Welcome back to SGLang Office Hour. We have two wonderful people from Anyscale today. Jeffrey, can you introduce yourself to us pretty quick? Yeah.
Yeah, hello everyone. My name is Jeffrey. I'm a software engineer working at Anyscale.
Can you talk about a little more detail, why you work on our inference? Like, what's maybe some journey stuff, anything?
Yeah, totally. So yeah, before joining Anyscale, I was actually at like some big corporate, and then working on serving machine learning models, and then machine learning infrastructure. And then I feel like Anyscale is a good fit for me personally to explore more into like the state of the art orchestration systems, LLM inference, as well as like I have the opportunity to go deep into the inference engines, for example, SGLang. So yeah, I personally feel that this is a good fit for me.
Perfect. And we also have Xinyu. He's a member of technical staff from Anyscale. So Xinyu, can you introduce yourself to us?
Hey everyone, I'm Xinyu. I previously graduated from CMU, Carnegie Mellon, and I went to like big tech, Meta after graduation, and I was like kind of exploring the AI agent space. Well, like the traditional tech is kind of boring, so I started to be a founder after graduation from Meta, and I was working on the like AI for working and future of work agents, but I found out most of my revenue has to go into like the token cost. Therefore, I started to explore like open inference engine like SGLang thereafter, and I thought like SGLang was one of the best serving engines for large language models, and therefore I got my connection with the SGLang people. And Ray was actually at the center of GPU and CPU orchestration, and I was able to talk with Robert directly, the founder of Anyscale, and I was deeply impressed by his passion. So I decided to join Anyscale and join the special squad team to improve like the frontier models with their better infrastructure.
Amazing. We actually collect like one question from the community. They want to know, like, as like someone who work on AI infra right now. So what like AI tool you're currently using? Like, what's the developer tool you currently like relied on every day?
Yeah, I can start first. So pretty biased because I work at Anyscale, so I have to say like I kind of like use Anyscale as the AI platform quite a lot because kind of like personal opinion. Anyscale, as you probably haven't or have heard about it, is like orchestrator and AI runtime for any of your Ray jobs. It allows like the data curation for pre-training and also for like the RL running time at the post-training. So it does really well in those two. And it also provides serving, which is like the what Jeffrey is working on. You can serve large language models on Anyscale as well. And Anyscale also like runs on any kind of neo cloud on top of Kubernetes. So it's cloud agnostic. As long as you have like your GPU cluster, we can manage your GPU cluster with Ray jobs pretty well.
Amazing. How about Jeffrey?
Yeah, I can add on to that. Yeah, Anyscale for sure, because that's for my day-to-day development. But beyond that, yeah, for Anyscale specifically and Ray specifically, we will be diving deep into the details later. But beyond that, cloud, I guess, cloud code, like dangerously skip permissions always on for me. Yeah, and like the like max effort always on. Not always. Maybe sometimes during planning, I turn down the effort a little bit. But yeah, I'm actually. I hope that the Mythos model would be released, but not now. But we'll see. Yeah.
Yeah. All right. Yeah, I think we should get started. So today we have a topic like about scaling LLM serving with Ray and SGLang. Again, we have Jeffrey and Xinyu in the house. And Jeffrey, I think you have the stage right now. Welcome.
Yeah. Thank you, Kai. Yeah, so today, Xinyu and I will be talking about scaling LLM serving with Ray and SGLang, and we will be talking about why do we care about Ray at all. Yeah, so let me go to the next slide here. So yeah, as I have introduced myself, my name is Jeffrey, software engineer at Anyscale. Xinyu?
Yeah, I work on scaling RL and infrastructure with Ray at Anyscale, working on collaborating with frontier AI labs and also like community open source like SGLang to develop better AI infra.
Yeah, for me specifically, I work on the Ray Serve team and also LLM Serving. So yeah, let's go into the content. So here's our agenda today. We're going to talk about what is Ray, why do we care about Ray at all, and then we'll have two deep dive sections. One is SGLang Ray backend, why we want to have Ray inside SGLang, and then the third section we will be talking about Ray Serve plus SGLang, how we use Ray as the control plane orchestrator to orchestrate SGLang engines across the cluster to scale LLM serving. And then we'll wrap up with some demo and the roadmap ahead. So yeah, Ray, it is really good at heterogeneous cluster. It's really good at serving, and it scales really well. And the major benefits that you get from Ray plus SGLang is that it offers scalability, fault tolerance, observability, and most importantly, with Ray, you don't need to manage a lot of YAML files with Kubernetes. all of the infrastructure is Pythonic. It's very easy to customize to adapt to your workloads, to your applications. And we'll be talking about why, like how Ray enables all of these capabilities in the following slides. So what is Ray? So Ray is an actor framework. So what is an actor? It's basically distributed stateful Python processes. That's all. That's Ray actor. You can spawn Python processes remotely on different nodes across the cluster. And as you can see in the diagram below, basically these worker processes, they scatter across the cluster, and these are Python remote processes and managed by Ray. And Ray is really good at resource allocation. So when you spawn these remote processes, you can basically specify, hey, which node I want to spawn these processes on what kind of hardware. It could be CPU, it could be GPU, it could be any type of accelerator. And Ray does so with what we call placement groups. And this unlocks the capability of heterogeneous compute pipeline. So it's very common in modern machine learning workload that you need to do some pre-processing, you need to do some GPU accelerated models, but not all models need the most expensive hardware, right? You can use L4, you can use H100, and it's very easy for Ray to configure and compose this kind of pipelines together. Next up is data movement. It's mostly through Ray remote calls. Like you want to pass data around between CPU stages and GPU stages, and it's very easy for Ray to do it. And failure handling, like we definitely want fault tolerance for production environment. And this is done by the global control store. If you look at the diagram on the left, it lives on the head node. You can think of it as the control plane of a Ray cluster. And then, yeah, as I emphasized previously, all of these are Pythonic. You don't need to manage your infrastructure. It's very agent-friendly, easy to configure, easy to iterate on. So yeah, today we're going to talk about like how we are using Ray to scale SGLang deployments, and this is an architectural overview of what that will look like. First off, you need a Ray cluster, and this could be open source kubeRay, or you don't want to manage infrastructure at all. You can use Anyscale. And then now, here's RayServe. RayServe comes in now. It is responsible for replica scheduling, orchestration, and request routing. And in the case of SGLang plus Ray, SGLang lives inside the replica. And RayServe is the control plane, the orchestration plane to orchestrate SGLang engines, as well as routing the request, as well as like bringing up replicas, tearing down replicas. Yeah. And then now, diving a layer deeper, there's SGLang. And SGLang has like great primitives for like scheduling, for example, speculative decoding, chunk prefill. Those live inside the RayServe replica, and you don't miss them by using Ray plus SGLang. Next up is Ray backend. That Xinyu will be talking about more, like why we even want to have Ray inside SGLang. What does that mean? But at a higher level, it enables granular Ray actor placement across the cluster. Finally, inside the engine, inside the Ray backend, it touches SGLang again, and SGLang has great primitives for attentions, kernel optimizations, like radix attention, for example. So here I want to emphasize that you are not losing anything from SGLang, but you're also getting the benefit of like scaling from Ray. So yeah, I'm going to hand it off to Xinyu to dive deeper into why we want to introduce Ray inside SGLang and what capabilities that it unlocks.
Okay. Cool. So yeah, when I'm talking about Ray backend instead of SGLang, okay, first don't freak out. It's not gonna take away the original MP backend. So Ray backend is an addition that is totally not intrusive, and it's an addition to the already existent MP backend, and it serves at the engine level, and it does not break any of the existing features you are already familiar with at SGLang. And here, starting from here, I'm going to talk about what we have already got from the MP backend. So here is like a 3-node setting with TP equals 8, PP equals 3, and you want to serve a K2 model. It's a 1 trillion parameter model, and you need 3 H100 nodes to serve this model. And look at here, we have to run the serving command on every single node in order to serve up this like large model. And for each command CRI, we have to input like the node rank, we have to input the host IP, and we have to configure all of this manually. So yeah, and like we have to run these 3 serve commands on 3 separate nodes, which is quite a lot of work. But thinking about the Ray, it looks like the same when it compares with the MP backend versus that you only replace the multiprocessing backend with reactors. But why would we do that? So one benefit is Ray is aware of the node's IP addresses. You can use the Ray utilities to get the node IP directly from each remote node, which is pretty convenient. You no longer have to manually see and configure the IP from remote nodes anymore. And second, Ray creates placement groups. And these are like GPU and CPU configurations you set into each remote node. For example, I want all of the TP ranks to live in the same node versus like TP or PP mixed together. So that is the benefit of Ray aware of the GPU topology instead of each node. And third, we have like the Ray scheduler actors using this remote actor to schedule all of the GPU workloads into each GPU instead of each remote node, which is more convenient than multiprocessing. So with all of those 3 benefits, we can right now serve the entire like Kimi model on 3 nodes with only 1 command by adding the suffix use Ray and remove all of the trivial manually configured parameters from the existing command line. So it's much more clean and much more easier to configure right now to serve the model. This is the best of like 2 worlds. And second, let's get more advanced to talk about the data parallel. So data parallel is a little bit different compared with the like TP and PP because we need to have like parallel engines run in different like nodes and configurations for the SGLang setting. So for the MP backend, we need like the data parallel controller to live in a separate process because we have to make sure like all of the scheduler process have the parent to be like a process instead of a thread. And the reason we have to do that is because if you like spin off the like scheduler processes from a thread, it's gonna mess up because there are so many things living at the engine side. The engine has like the tokenizer, has the ZMQ management, and it has a lot of things inside of this process. And if we directly spin off the like scheduler process from engine, it will like be very dangerous because it inherits a lot of unnecessary stuff. And for Ray backend, it's just more convenient because reactors are actually controlled by global control store managed by like Ray itself. It doesn't have to go through the multi-process, the inheritance line as the MP backend, which makes it more cleaner and lightweight than MP backend data parallel controller to spin off scheduler actors. And let's look at this in greater detail. Like, first of all, if you want to create a multi-process, you have to like spin off like a lot of like peripheral stuff, like the pipe, and in order to communicate with the child process and start it and append it and manage it in a parent process. And second of all, you have to also spin off the scheduler process instead of the parent data controller process, which is another layer of process. And it's very heavily managed inside of the data parallel controller. Versus Ray, it's much cleaner since you can spin off a thread with like a data parallel controller as a thread. So the number of lines you have to write is much less. And also, it requires just like a reactor to spin off the entire scheduler actor from the data parallel controller, which is managed by GCS, Global Controller Store, which is managed by Ray versus the parent process. So what is the benefit of all that except for the concise code? So first of all, let's look at how much cost if you run at the MP backend. So if you create a child process and the child process cannot dangle, it has to listen to its parent. So if its parent dies, the child has to die as well. So in order to keep its child living, we have to make the parent living. So inside of SGLang MP backend, there is like this 30-day sleep anchor thread that keeps the parent living in order to keep the child living, which is pretty counterintuitive. Versus Ray, as the schedule actor in Ray is totally managed by Ray, that is GCS itself. We don't have to worry about the liveliness of the parent process or the child process at all. So second, the parent process doesn't have to manage like the child process anymore. So in MP backend, you have to kill yourself if your parent process dies. And in Ray, as this is all managed by the Ray cluster, you also don't have to worry about this. And third, because like all of the remote nodes in multi-process background have to are unaware of each other. So we have to manually broadcast the ports to each single node in MP backend. And versus Ray, all of this is managed by Ray cluster. So with all of those benefits, like we have even more to come with the Ray dashboard, which is observability. For each reactor we create, we can monitor them pretty live with the GPU memory and CPU resources consumed in the Ray dashboard. This gives you awareness of which actor could have died or not going well, and you can understand like which process each reactor is running. And also you can look at the stack traces of each reactor by looking at the profiling, and it makes like the entire inference engine easier to debug. With all of those benefits, Ray does not bring any major regression, as we have run quite a lot of benchmarking to compare the Ray actor backend with the MP backend. Running even like the large models, MOE models with like TP and EP, Ray brings no major regression for the performance. You can use Ray backend pressure-free. And last but not least, we can benefit like the RL reinforcement learning by giving you the example of Miles. So as Miles is also a part of the project of Ray's Arc of the SGLang community, we are working heavily on bringing more benefits of the Ray backend into the like Miles framework as well. So you can see, so if you are doing like weight transfer, like the inference engine, which is SGLang, and the trainer, which is like probably Megatron, they have like different topologies. So for trainer, you have like TP equals 4 and PP equals 2. And for rollout engine, you have like TP equals 2. So like these two models are running at different model parallel. So in order to transfer the weight, the trainer model has to be aware of the topology of the rollout engine model topology. So with like Ray backend, we can very easily pass this parameter or pass the model topology through the Ray remote call. And after like the trainer model is aware of the inference engine like model layout, we can also start to sync the model weight directly from the trainer to inference engine powered by redirect transport. This is like zero copy GPU to GPU direct memory transport through Nixle. And with one single call, you can pass all of the model weight from the trainer to the inference engine with Ray-backed RDT. Yeah, then I will pass it to Jeffrey to talk more about Ray Serve plus SGLang.
Yeah. Thank you, Xinyu. So now I'm going to dive deeper into, now we understand why Ray is inside SGLang, because we want like granular placement, we want topology or Ray scheduling. Now I'm going to talk about what is Ray's role outside of SGLang. So what is Ray Serve at all? So it's a scalable model serving framework. It is a orchestration framework orchestrating replicas and route requests across a Ray cluster. And here I'm going to introduce some of the most important components inside Ray Serve so that you can understand a little bit more about the features that I'm going to introduce later. So first off, we have the controller on the left-hand side on the head node only. It is the most important component inside Ray Serve. You can think of it, Ray Serve is basically like a reconciliation loop, and the controller drives the current state towards the desired state. So that's the controller's role. And inside Ray Serve, we have like replicas. In terms of SGLang plus Ray, SGLang engines live inside these replicas, and they hold their own like request queue. And deployment, you can think of it as a abstraction layer for these replicas, and it also maintains a version config, which the controller will drive its current state to the desired state. And now we have proxy. It could be HTTP proxy, it could be gRPC proxy, but regardless of whether it's HTTP or gRPC, their role is to terminate HTTP request or gRPC request, and then it also holds a route table to find the appropriate, the corresponding deployment handle, find the deployment, and then send the request to the deployment. So why do we care about Ray Serve plus SGLang? First of all, it's Pythonic, it's easy to iterate, it's easier to configure, it's easy to set up. Second of all, customizability. There are some features, for example, custom request routing that we'll talk about what we use custom request routing for. Custom auto scaling as well, and Ray Serve also has this multi-model capability. You can easily compose a chain, a DAG of models together with Ray. Next up, fault tolerance and observability. So to put it into the picture of architecture diagram, now we're going to talk about Ray cluster, like how do you set up a kube Ray cluster? And it's very straightforward. You install KubeRay on your Kubernetes cluster, and then you can get Ray. You install these CRDs along this Helm package. Or if you don't want to set up a Ray cluster at all, you can use Anyscale $100 free compute credit. Next up, Ray Serve. This is where Ray Serve lives inside the cluster. You can see that it's bounded by these blue rectangles. There's a serve controller that I talk about in the head pod, and in the worker pods, there are like proxies, ingress, and replicas deployments. And I want to highlight that ingress. This is very specific to SGLang plus Ray Serve, and its role is to validate and parse OpenAI compatible requests, and then dispatch the request to these deployment handles. So this is how it looks like in code. First of all, you specify SGLang server in the server class. Next up, you specify engine parallelism configuration. So it's, for example, like TPPP. These are standard. These are identical to SGLang engine keyword arguments. Next up, you need a placement group. This is where you direct the SGLang Ray engine to spawn model runners on the correct placement across the cluster. And you give it like appropriate resources. Finally, any configuration that are general in Ray Serve still applies here. So for example, autoscaling configuration, you can configure your own autoscaling policy. And this entire example, it will scale logical model replicas, TP4, PP2 in this case, as a unit. So this is how Pythonic it is with Ray. And I want to contrast it with Kubernetes native leader worker set. You will need to manage a lot of YAMLs. It's not very agent friendly, not very easy to iterate. Yeah, and now I'm going to talk about customer request routing. So this is one of the important features in Ray Serve that is very useful in LLM Serving. So what is customer request routing? So when the request is dispatched from the HTTP client, it reaches the HTTP proxy on a Ray cluster. And then, as I mentioned earlier, the proxy itself maintains a route table. It finds the relevant deployment handle, runs the request router among these replicas, and then choose a replica to dispatch the request to. And you can, and this request router is customizable. You can do so by using this config, request router config in the serve.deployment decorator. And in particularly for LLM serving, you want to make use of the prefix cache in these replicas, SGLang replicas. So in Ray Serve LLM, we maintain a prefix tree. So we customize this router to look up the prefixes in this prefix tree and find out the associated replica and dispatch the request to that replica. So in this case, replica 2 has the prefix cache, the matching prefix, and this router, prefix cache affinity router, will dispatch the request to that replica. And there are some trade-offs here. For example, why we choose to use a single prefix tree actor. This is because it maintains a universal view of all of these replicas, and then we don't need to subscribe to KV events emitted by these engine, so that this router stays engine agnostic. It could be applied to SGLang and other LLM frameworks. And this is how you will do it in code. You specify the request router class to your customized router, in this case, prefix cache affinity router. And there are some other knobs that we provided for you to tune the eviction policy, the load balancing policy for this router. Next up, custom auto scaling. and I'm going to walk through how does it work. So for deployment replicas and deployment handle, they maintain their own set of metrics. So for example, for replica, deployment replica, it has a local view of its request queue, and deployment handle will have a universal view of what requests have been accepted but have not yet been dispatched to these replicas. So these metrics will be pushed to the Serve controller through RPC, and the controller will basically derive a target state by taking these metric as input and the policy, auto-scaling policy, to derive the target state. And the deployment state manager inside the controller will drive the current state towards the desired state. And this is how it will look like in code. You'll have policy, auto-scaling policy under this auto-scaling config. Inside this serve.deployment decorator. And this is particularly useful, for example, if you want to do predictive scaling, you want to scale based off of the time of the day, or you want to integrate some more advanced scaling policy. For example, you want to take TTF-TT pod as input. And this also gives you the knob to set max ongoing request to your critical batch size. So you profile your GPU, your workload, and identify a suitable batch size, set max ongoing request to that batch size. Next up, we have model composition. So in modern machine learning workloads or serving systems, LLMs themselves do not operate in silo. Most of the time, they need to collaborate with other models. For example, in a typical recommendation system, you will have pre-processing, you'll have retrieval where you retrieve a set of candidates to rank from, and then you apply LLM re-ranker to rank these candidates, and finally you apply business logic during this post-ranking stage. And as I mentioned earlier, that these are very easily composable with Ray. You basically define these stages as ordinary Python classes, decorate them by serve.deployment, give them some configuration, resource configuration, auto-scaling deployment and configuration, and then bind them all together on the right-hand side right here through this bind function call. And now we have fault tolerance. Ray is also good at handling fault tolerance. So for example, if replica dies, the controller will restart it. If the proxy actor dies, the controller will restart it. If the controller dies, Ray will restart it. And if Ray dies, if you configure GCS with high availability with an external cache, for example, Redis, it'll also back up the cluster state for you. So if you take a look at this right-hand side diagram, here I want to highlight that you can configure proxy with high availability. And what that means is that the proxy will not only live on the head node, but also will live across the cluster on all worker nodes. So a good thing about that is when one of the proxy dies, you can keep serving HTTP requests. So now that we have concluded some of these features, custom request routing, custom auto scaling, fault tolerance, now I'm going to walk you through a demo to demonstrate observability inside a Ray cluster, and then talk about our roadmap ahead. So let me play this. So yeah, so here we basically have these configurations, and then you basically, so this YAML file is different from the Kubernetes YAML file that I mentioned earlier. Here we only need to specify application logic, application configuration, but not infrastructure. So for example, you have auto-scaling config, you have like engine arguments pass through SGLang, placement group config to define where you want to place the Ray actors inside the SGLang across the cluster. You hit serve deploy, and then here's the open source Ray dashboard that you can look into. So you can see that it's starting a proxy, it's starting like auto-scaling with auto-scaling. It has this OpenAI ingress, it has SGLang server. This runs inside a replica. And then now I'm just sending traffic. And I'm sending a specific shape so that it kicks off auto-scaling. And you can see that inside this replica log, you can see that it's hitting this chat method. And then if you look at the OpenAI ingress, it's hitting the, hold on, it's too fast. Okay, so it's hitting V1 completions OpenAI compatible endpoint. And this is the traffic shape that I'm sending to the deployment. You can see that it's auto-scaling the replica per deployment. And there are some other like typical serving metric that you can look at, like latency, ongoing HTTP requests, for example. Yep, this is all for the demo. So yeah, just to summarize, we have covered a lot of interesting topics today, but I want to emphasize that Ray and SGLang, they are not conflicting. They are complementary layers. Ray is responsible for orchestration, the control plane, and SGLang is responsible for executing the model with all of those great primitives like radix attention. Ray, internal to SGLang, it determines the actor placement and it determines actor scheduling. And the benefit from it is that you can get granular placement. For example, for RL, you want to schedule the Ray actors on, like for training an inference engine, you want to schedule them differently. And then observability and fault tolerance also come out of the box. Ray, external to SGLang, it is the orchestration framework. It does replica orchestration. And Ray itself, it's very easy to customize. You can adapt any of the components, not any, but some of the components that I introduced today with your own application logic and your use case. And it's Pythonic, it's very easy to iterate on, and observability and fault tolerance also come out of the box. Yeah, so before diving into the roadmap, I want to thank these guys for your contribution to Ray, Serve plus SGLang, particularly for this work stream. Yeah, and these are like great folks to work with. And thank you all for your contributions, and looking forward to more. So here are some roadmap items that we have in mind to specifically for Ray plus SGLang this work stream. First of all is observability. Now we don't have full observability into SGLang engine metric in Ray dashboard. That's something that we want to enable. For example, TTFT, TPOT, KV cache utilization. Yeah. Next up is prefill disaggregation. How we place, prefill, and decode SGLang instances, and how we connect them in Ray. Next up is wide EP. This is a very typical serving pattern for MOE models. And finally, reinforcement learning. This has become very popular in recent days, how we want to place SGLang engines for RL. Yeah, so feel free to reach out. We're looking to work together with you to grow this community. Seiji is also on my team. He's not here today. Xinyu and I, these are the QR code to our LinkedIns. Feel free to reach out, feel free to connect. And then here's the top level roadmap item GitHub issue that we are tracking. So I'll give, I guess, like 30 seconds for you to scan these QR code if you are interested in. All right, yeah, I'll also be sharing out the slides. So if you didn't get it, if you are driving, that's all right. You can scan it afterwards. And then finally, please join Ray Slack. And we also host our own office hour, Ray LLM Office Hour, bi-weekly on Tuesday. And the next one, we'll dedicate it to discuss Ray, Serve plus SGLang, like the roadmap items that we have. And we want to work with you together to grow this and then to scope out the details. So please join us next Tuesday, 10 to 11 a.m. PDT. So sign up here to get the invitation. Yeah, that's all from us. Thank you so much for listening. Kai, back to you.
Yeah, this is amazing. I love the detail you share and also how you inside the community to do the contribution. Yeah, let's do the Q&A right now. I think we can wait to see if we have some question from the community.
Yeah, feel free to also reach out to us on Ray Slack. If you are shy to speak up here or pose any questions, we're happy to answer.
Hey, while we're waiting for the question, I would love to know. So, can you share one or two use case of Ray in production, stuff like that, so people would know what would be the good case to use Ray?
Yeah, totally. So I can start. I've heard from customers a lot that why they want to use Ray Serve in production is that it's very easy to do these kind of model composition, because most of the time you are operating like a lot of models. You want to do A/B testing. You want to switch models. You have this workflow, like for example, for recommendation system, you have a series of machine learning models, right? And then LLM also fits inside that picture, but it's very easy to individually scale these model and pass the data, pass the requests around these models. So that's one use case. Xinyu, do you want to add anything?
So when we are collaborating with frontier labs that are doing model training, one of the most popular use cases is for data pipelines. For example, a lot of the open source data frameworks are built on top of Ray. For example, the data juicer, Nemo curator for video pipeline generations, and for batch inferences. So we see a lot of people trying to build up their data processing pipelines on top of Ray. And also for post-training, there is a recent survey about from Hugging Face that mentioned 8 out of 16 the most popular RL open source projects are using Ray as the backend for orchestration. And yeah, I think we see a lot of very good open source projects that are using Ray to scale and build their data pipelines.
That's amazing. We have a question from the YouTube.
Yeah.
How does Ray Serve handle the load balancing of KV cache across multiple SGLang instances?
Yeah. So let me take this one. So SGLang itself builds up the KV cache, right? And Ray specifically, it uses this custom request routing. It maintains a universal view of prefixes, and it basically, when you have a request, it matches a certain prefix. It knows which replica to go to, and it will dispatch the request to that replica.
I also have one following up question. So, does Ray only like do LM? Does it do like diffusion model? Does it do, like audio language models, stuff like the TDS, stuff like that?
Yeah, totally. So Ray Serve, Ray in general is not, it is model agnostic. It can do anything, but there's no native integration right now. Like comparing to Ray Serve plus SGLang, there's no like native integration right now for diffusion models, but that's definitely something on the roadmap to provide native integration, native API, Ray API that you can call into SGLang, for example, SGLang diffusion models.
Great, that's good to know. Yeah, let's wait to see if we have any like more question in the community for 2 or 3 minutes. Maybe I can ask one more. Like, oh yeah, we got something from the community. So Shivan like asked how to get started with such a massive code base. Maybe are you talking about Ray or are you talking about SGLang?
Probably, hey, I could just
Go ahead, Joe.
example from like the integrating Ray backend into SGLang perspective. I think, yeah, like it would be great if we can get like reviewers from the SGLang contributor community to give you like some help and guidance. Join a Slack and Discord if there's anything particular you're interested in, and get the right person in contact would be the first step. If you have like someone great to review your PR, if you want to be a contributor. But if you are just like exploring the code base, I think you could probably look into like small feature. I think for SGLang, there's like a mini SGLang project that is like copy of the SGLang with much less code. You can get handle of it like much quicker. And for like Ray, I think you can start with like using it instead of directly diving into the internals of it, and understand what kind of use cases it provides before like get hands into like the code. And the other thing is, I think navigating through coding agents is so much helpful. So right now I have like literally the habit of reading code through coding agents instead of directly navigating through the code base. I just ask like, hey, how does SGLang implement prefix caching? And I work through, and I ask the cursor or cloud code to give me like a walkthrough, like by like providing a tutorial, so I can follow much easier. So that is like my experience in like navigating through massive code bases.
Jeffrey would like to share or like?
Yeah. I pretty much want to resonate on Xinyu's last point about coding agents. What I do is git clone the repo and throw everything to the coding agent and ask it to tell me like answer my question basically. Another thing that you can do, like start with some good first issues, but what you can do is you can ask the coding agent to read these issues, ask it to provide an implementation, but not post it just yet. You look through the implementation, ask it to explain why it is implementing, why it fixes these issues in this way, so you understand like how you would do it by yourself. And then maybe some coding agents, they will make some mistakes and you can now chime in to iterate. So that's something like getting started with the coding agent is something that I personally do as well.
This is great, and thank you, Xinyu, for mentioning Mini SGLang. This is a very good project that we designed it for learning things pretty quick about SGLang. Yeah, and I think one last question that we have from Colin, I guess. Do you have a quick comparison of Ray Serve performance overhead on VLM with SGLang?
Xinyu, do you want to take this one?
So I think like for Ray backend side, there's no like static like regression. So I think for Ray Serve specifically, I think it's more on the Jeffrey's side to answer.
Yeah, so we have not done any like VLM plus Ray, we have done VLM plus Ray, but not VLM plus SGLang. We have not compared with VLM yet.
Great. Yeah, I think we should close the Q&A right now. So let me quickly talk about things about SGLang. So if you haven't like follow us on GitHub and started on GitHub, please do. And also like please follow LMC Historic on X. So basically we share everything about SGLang on this account, including like day zero model support, like Gemma 4 and the QM model that was launched today. So last week, 2 weeks ago, we launched courses with Deep Learning the AI. So it's a little bit over 1 hour. It's going to talk about some basic information about how inference works with SGLang, how caching works with diffusion models, and we are going to quickly talk about how AI inference is headed and what comes next. And this is the QR code for the Deep Learning the AI course. And we have a Luma calendar again. So basically, we will put all the meetup and also all the bi-weekly office hour on that. So follow that, you get notified by Luma. All right. Thank you so much for your time for two speaker, and see you in the next office hour. Thank you.
See you guys.